All right, let's start today's lecture, the second lecture from Konstantin Zarembo.
So let me remind you what I was talking about yesterday. Introduced n=4 superring mills. It's a quantum field theory in 4 dimensions with this Lagrangian. And it is a conformal theory, so the natural objects to consider are local operators, and we will consider single trace operators, which are characterized by their spin and scaling dimension. So scaling dimension can be read off from a 2-point function. And, well, let's consider a simple example. So some operator that we can immediately build from the fields is a mass term for scalars. And it has a name, it's called Cauchy operator. So we take the square of phi, sum over indices, and take a trace. And obviously, this is an operator of dimension 2. Because scalar has, each scalar has dimension 1, so in total, this should be an operator of dimension 2. So let's check it explicitly by computing a 2-point correlation function. So the leading order diagram is just this one. And OK, so we need to take into account some symmetry factors. So there is an overall factor of 6 coming from summing over SO6 indices. There is a symmetry factor of the diagram itself, which is 2. So the easy way to understand it is that before you draw the diagram, like if you just draw the 2 vertices. For the operators, there are 2 ways to connect them, like this, and then you can also rotate and connect. This gives the same diagram, but in terms of V contractions, these are different ones. So there is a symmetry factor of 2. And then further, it's a one loop diagram, so it's of order lambda squared. Well, OK, so there is a factor of lambda from each of the propagators. So in total, we have a factor of lambda squared divided by, yeah, so let me write this as a square of the propagator. It's lambda over 8 pi squared x minus y squared squared. So in total, I get 3 lambda squared divided by 16 pi to the 4 x minus y to the 4. So this prefactor is not important. We can absorb it in the redefinition of the operator by normalizing it with some lambda-dependent factor. So what is important is dependence on the distance, and it indeed comes outright. So it's goes as 1 over x to the 4. So, well, yes? So, what should I say? So in principle, that's a definition. That's a definition. So you have some sum of diagrams, and they would produce some scaling dimension. But of course, there is just a dimensional analysis, simple dimensional analysis that scalar field has dimension 1. This guy should have dimension 2. So, and it works.
Thank you.
But let's see what happens at one loop. So at one loop, well, we just decorate this basic diagram by all possible loop corrections. So we need to insert, we can insert one scalar vertex in the middle, plus it is possible to exchange a gluon between the scalar lines. But also the gluon can connect to one and the same line. And well, there will be also other corrections to the other propagator corrections. So all of them need to be summed up, and we will get some result. I will leave you this calculation as a home exercise. It's well, it's not very simple, not very complicated. I mean, but one feature that one can see immediately without doing any calculations is that you will get an answer that will contain a logarithm. So let's insert one operator at point x and the other at 0, and then there will be an intermediate point of integration, which is y. If, for instance, in this diagram, we will need to integrate over 4-dimensional space the product of 4 propagators, so it will be x minus y to the power 4, and then y to the power 4. And you see this diagram, this integral diverges logarithmically when y is very small, namely when y comes very close to the insertion of an operator, and the same happens when y is very close to x. So when it comes to insertion of another operator. So this diagram is easy to see that it scales as 1 over x to the 4, which is the right answer, right? Because there are 4 powers of distance in the numerator and 8 power in the denominator. But it will also diverge. So we'll need to regularize it. And well, since it diverges logarithmically, it will be proportional to the logarithm of the ultraviolet cutoff. And ultraviolet cutoff has a dimension of momentum, inverse length. So by dimensional analysis, this has to be multiplied by something of dimension of length, and the only length scale in the problem is the distance between the operator insertions. So what we'll get is a logarithm of lambda and x. And let me write down the result of the full calculation. So so to one loop accuracy, what we'll get is 3 lambda squared over 16 pi to the 4 x to the 4. 1, this is the 3-level answer, and then minus 3 lambda squared over 2 pi squared logarithm of lambda times x. And then this is the one loop correction. Of course, there are higher order terms. So taken at face value, it looks like violation of power-like scaling because you got a logarithm. But the way it should be understood is that so these logarithms, they have to exponentiate. So otherwise, this would be consistent with conformal invariance. So these logs will exponentiate. And this can be proven if you take some very old textbook in quantum field theory, like Bjorken and Drell. They will have a diagrammatic proof that such diagrams exponentiate. but this is the only possibility consistent with conformal invariance in this particular case. So, yes?
What does that mean, logs will exponentiate?
Sorry?
What does this phrase mean, logs will exponentiate?
Why does it need to exponentiate?
What does it mean?
Oh, so that this means that the next term will be logarithm squared divided by 1/2. So the 3-loop correction will be, we'll have a triple logarithm that's divided by 1/3 factorial and so on. And so if you resum the leading logarithms, what we'll get is an e to the logarithm with some coefficient. And that's the same as the, so as a correction to the power. So what we'll get is, let me see. So let's not take trace of the constants in front. We'll get something that depends on the UV cutoff raised to the power minus 3 lambda squared over 2 pi squared. And then absolute value of x to the power 4 and also minus 3 lambda squared over 2. There is no square here, it's just lambda. And no square here. Indeed, if you re-expand this in lambda, the leading term will be a logarithm. But written this way, it's consistent with the conformal invariance, provided that we also change the scaling dimension. So the operator acquires what is known as anomalous dimension, so the real scaling dimension of Kanishi is not 2, but 2 plus a small correction. In fact, so if I think now all the signs are correct, right? So writing it this way is the same as writing lambda x in the denominator. If you expand, this will be a logarithm with a minus sign, right? So so we conclude that to one-loop order, Kanishi operator has dimension 2 plus 3 lambda over 4 pi squared. So this is an anomalous dimension generated by loop corrections. So this is the mechanism by which scaling dimensions of various operators acquire dependence on the coupling constant. It arises because loop diagrams actually diverge. There's no contradiction to finiteness of superring mills, because finiteness only means that there are no corrections to the beta function. So the coupling constant doesn't run. But if you compute correlators, you need to regularize, and there will be divergences. And they should be somehow removed from the finite answer. So the way they are removed here is that we need to renormalize the operator by an infinite constant. So you see that this lambda-dependent part is just a coefficient in front of the operator. So if we define renormalized Kanishi operator by multiplying it with the z factor, so we take a bare operator and multiply it with the z factor. So if we choose z to be well, some constant, it's not really important, and then lambda to the plus 3 lambda over 4 pi squared, then you see that that this explicit power of lambda will compensate the divergence, and the correlation function of the renormalized operator will be finite. So an interesting and technically very important point to notice here is that this power is precisely the anomalous dimension. And it's kind of clear what goes on here. So we have a bare operator which has dimension 2, and it doesn't change with taking into account loops. But we need to multiply it by something that contains a dimension full parameter, which is simply UV cutoff. And that changes the power counting. So the dimension of the left-hand side is actually not the 2 because Z itself has a dimension. And another way to read off the anomalous dimension is to just look at the Z factor and see how it depends on lambda. So the anomalous dimension, let's denote it gamma, is simply Z minus 1 dz over d log lambda.
Sorry, quick question.
Yes?
Is it obvious that K has a 0, 1 point function?
Sorry?
Is it obvious that the Konishi operator has 0, 1 point function?
It's well, it is forbidden by scale invariance, but from the diagrams it will appear that it does a non-zero point function, which this diagram is in principle non-zero. It goes as lambda lambda squared. So these diagrams have to be subtracted. So in principle, one needs to normal order Konishi operator. Normal ordering, by definition, is a procedure that removes the 1 point function.
Right, okay.
So in principle, yes, that
So
this is.
Oh yeah, so there should be a minus, like something there. Okay.
Yes.
Okay.
So all right, and then the scaling dimension will be equal to the bare scaling dimension plus the anomalous part that comes from loop corrections. So the basic idea here is that the renormalized operator will include small distance effects that are dressing the operator itself. And then, yeah, that's something that. So renormalization is simply a way to absorb small scale fluctuations of quantum fields into the redefinition of the operator. And well, as a result, it changes its dimension. So any questions at this point? Then, yes?
I mean, maybe something I've missed. So in the Feynman diagram, the insertions are of Konishi operators.
Yes.
Okay,
Yes.
so
This is just phi squared.
Yeah.
Phi squared.
So the dimension of the Konishi is 2. So in the formula for the propagator, shouldn't it be x minus y to the 4th power?
This is what we got.
But that's with 2 propagators.
That's with 2 propagators, yes.
But shouldn't one be like 4?
Oh, so individual propagator has x squared, right? And that's why the scalar field has dimension 1.
Yeah.
So then we stretch 2 propagators between between the 2 operators, and this gives a power of 4.
But oh, phi is the propagator. Okay.
Yes.
Okay. Thank you.
Yes. So that's is important that this is a composite operator that consists of 2 fields. So then, well, we can consider more complicated operators. And when we do so, there is a new phenomenon that occurs, namely operator mixing. And I will exemplify it on operators, on generic scalar operators. So let's consider an operator that is built from L scalar fields with arbitrary SO6 indices. So actually, looking at these operators is a way to see what are strings in gauge theory. There's a very important observation by Bernstein, Maldacena, and Nastasia, who realized that if you want to see what is a string, you just consider an operator of very large length, and then it sort of becomes a chain with dense distribution of points, and renormalization of this operator is more or less equivalent to propagation of string in AdS 5 cross S5. So ideally, we want to be able to compute scaling dimensions of these operators, not just for arbitrary fixed number of fields, but also in the limit where the length of the operator becomes very large. So this is the problem that I will be talking about for the rest of the course. How one can nicely package this problem in the algebraic way that will reveal actually the hidden symmetries of the theory, namely integrability of n-equal 4 supernomials. Well, the diagrams that we draw are basically the same. So if we want to renormalize this operator, well, let me draw just one of them, and the others look basically very symmetrically. So one thing that you can realize is that most of the fields at one loop remain spectators, because to build a loop, we only need 2 scalar lines, right? And this diagram is just the same as for Konishi, with a small difference that now these 2 indices are not summed over, but are just arbitrary ones. So we start from some indices, I don't know, let me denote them by IL, and then the next index will be IL plus 1. But the indices that will appear in the out state are in general will be different. So we'll have some indices JL and JL plus 1, which are dictated by the structure of the four-scalar vertex that comes from the Lagrangian. So a question to you: why do I consider? I mean, these indices, they in principle can, take values from 1 to L. Why do I consider only nearest neighbors? Sorry? Yes, but in principle, I could connect any lines to any lines, right? These are all the same scalar fields. Yes? Yes, exactly. So, in principle, we should draw these lines in two-line notation. And if you do so, you will realize that interactions between nearest neighbors is the leading effect at large n. But if these lines are separated along the chain, to connect them, you need to go under the propagators, and that would produce non-planar diagrams. So planarity makes interactions, simplifies the story because only nearest neighbors interact. But okay, so we'll get a divergent diagram, and this has to be subtracted. But this subtraction is not diagonal. So this operator by itself will not be renormalizable. So this operator has a SO6 index. Let me denote it by, well, it's a vector with L entries. And then a renormalized operator, which will have indices denoted by J, will be equal to the Bayer operator multiplied by some matrix. So operators mix, and the Z factor becomes, instead of being a number, becomes a matrix. So the good question. It is, again, by planarity. So I cannot give, one needs to draw diagrams to see this, but if you draw a diagram that mixes single trace operator with double trace operator, you'll see that it's suppressed by 1 over n as being non-planar. So then the mixing, one can define a mixing matrix, which is a logarithmic derivative of the Z factor. And so to get the anomalous dimensions, one would need to diagonalize it. So the upshot of this is that good conformal operators will be linear combinations of the basis operators of the field monomials that one started with. So the operator will have a form which will be some tensor with L indices contracted with the field monomial. And so to make contact with string theory, it's convenient to think of this object as a wave function, so that gamma then is a Hamiltonian acting in some finite dimensional Hilbert space. So there will be in total 6 to the field monomials. And there is some matrix defined on this space that we'll call Hamiltonian. And the wave function, the tensor, which we'll call the wave function. So this wave function, it's convenient to think of it as a wave function of a spin chain. So we have, well, each operator is a circle. So this horizontal line is just a trace contraction. And then at each vertex, we have a 6-dimensional vector. So the Hilbert space in which the mixing matrix acts is basically the tensor product of L copies of R6. There is a small caveat here that the trace is cyclic. So in principle, we need to mod by cyclic permutations. But this can be imposed as an extra constraint. So we can, in principle, diagonalize the Hamiltonian in the full Hilbert space and impose an extra condition, which is very similar to gauge condition, that the wave function should be invariant under cyclic permutation. Yes? Well, I will describe this in a second. No, wave function, because it's a 5-dimensional object. It's just, I'm calling it a wave function, but it's in practice just a tensor with L indices. Yes? So the logic here is the following. I start with the operators which are just monomials. But then if I try to renormalize them, I realize that they mix. So that there is that the Z factor that subtracts divergences is actually a matrix. So, but that's not what we want. This means that the operator mixing means that operators are not renormalized multiplicatively. So we are adding together apples and oranges, or objects that have different scaling dimensions. So if we diagonalize, we are back to the situation where all renormalization is multiplicative, and then each operator that is an eigenvalue of the mixing matrix has a definite scaling dimension, which is simply the bare scaling dimension plus gamma n. And this L0 is just the length of the operator. So that's the logic. We want to find the basis where the operators renormalize multiplicatively. And this is done self-consistently. We first need to figure out what is gamma, then diagonalize, and then we have the set of operators that are nice. So for that, we will need to compute the mixing matrix. And this is, well, I mean, for that, let me just draw pictures. I'll prefer to draw an operator not as a point, but as a line, where each of the points is the scalar field with certain indices, I1, I2, etc. And then somewhere I insert a loop, right? So these indices will somehow reconnect and become, well, so these indices will continue as they are, but these indices will be changed. So whereas the rest of the indices will be left intact. So if one does a calculation, so this diagram is simply a four-valent vertex that comes from the Lagrangian. I will not repeat this calculation here, but it is not very difficult to see that the Hamiltonian, or actually the mixing operator, or the mixing matrix acting on elementary sides has four indices. Let me call them I, J, K, and L. So this would be I, index I, K, and they will become J and L. And H will act on indices I and K, and in the out state we have indices J and L. So if one carefully reads off what comes from the Lagrangian, then one finds that this has the following structure. It is proportional to delta Ji, delta Lk, minus 2 delta Jk, delta Li, and plus delta JL, delta Ik. So if we trace how the indices flow, then this term would naturally be interpreted as the unit operator. So the indices do not change. So here the indices change places, right? So if this was I, J, L, K, so here I becomes L and K becomes J. And finally, in this term, the indices in the in and out state are contracted. So one can call this matrix a permutation matrix, and and this will be a trace. So at the end, what you'll find is that the mixing matrix is equal to lambda over 16 pi squared, and then sum over all nearest neighbors of 2 minus 2 is permutation acting on sites L and L plus 1 plus trace acting on the same sites. Yes.
I'm not sure if I understood why they had to be nearest neighbors. Like, why can't you just trace IL plus 1 with I3, J3 or something like that?
That's planarity. It's just, if you
Okay.
look at the diagrams, then you see the diagrams that mix fields that are far away and along the chain, then these diagrams are not planar.
Okay, thank you.
Just write them with double lines, you will figure out.
Yes. Okay, so for this to not look very too abstract, let me give an example, and just let's compute the Kanishi anomalous dimension from this point of view. So Kanishi you can write as delta ij trace phi I phi j. So now this is psi, right? So the wave function for Kanishi is simply the delta symbol. The length is equal to 2. And we need to act by this operator on the wave function. So permutation acting on psi is equal to psi itself, right? So it's symmetric in the indices. And trace will contract the indices and reinsert the delta function. So contracting the indices gives a factor of 6, and then we'll get the same psi. So in total, when we act by gamma on the Kanishi operator, we need to take into account that there are two links in the spin chain. So there are two vertices, but the Hamiltonian is defined on links. So there will be a factor of lambda over 16 pi squared, then a factor of 2, because there are two links. And then we need to read off just the eigenvalues of each of these operators. So because they are all diagonal on this wave function, so this factor can be seen to cancel, right? So this will give, so permutation has an eigenvalue 1, so this part of the Hamiltonian doesn't act at all. And this term gives a factor of 6. And so this is the anomalous dimension of Kanishi, which can be seen to be equal to 3 lambda divided by 4 pi squared, which is the correct answer that we got from computing one loop diagrams.
The wave function denoted by k is the same as psi, right?
Sorry?
The wave function denoted by k there.
It's psi, yes,
psi,
it is psi. So, yes, let's call it psi. So just the tensor that's simply delta ij. Another important example is that of chiral primary operators. So chiral primary operators are states in which in which the wave function that contracts the indices is traceless and symmetric. So chiral primary operators are ground states of the spin chain. So the Hamiltonian annihilates the wave function of CPO because okay, so because they're symmetric, this part of the Hamiltonian cancels, and they're also traceless, so taking a trace also produces 0. So they belong to the same, for a given length, they belong to the same SO6 representation. So essentially there is one operator and all its partners on the SO6 rotations. And as said, they are the ground states of the spin chain. They're also related to spherical functions on S6. So you can define a function of unit 6-dimensional vector by contracting traceless symmetric tensor with the components of the unit vector. And so the important property of these functions is that they are annihilated on the Laplacian they are not annihilated, they are eigenfunctions of the Laplacian with the eigenvalue that's equal to L plus 4 if I remember correctly. So somehow the spin chain that we got knows something about S5. Its ground states are in one-to-one correspondence with spherical harmonics on S5. Yes. This is y as a function of a unit vector. It's a function on a sphere. N is a vector with n components constrained to have unit lengths with 6 components.
You can press the chalk better because it's hard to see from here.
I'm trying. It's somehow I'll try to write more clearly. So in fact, this non-normalization property of chiral primary operators extends to high loops. One can show using supersymmetry that they're not renormalized at all, so that their scaling dimension remains to be coupling independent to all orders in perturbation theory. So the real question that we want to ask, and it's a hard question, is how to compute the full spectrum of the mixing matrix. And this question is difficult even at one loop, because if you think physically of what this operator represents, it's an operator that shuffles spins on a one-dimensional chain. So it's a typical problem that one encounters in condensed matter theory, where you have some collection of spins that are living in one dimension, and then they interact locally, so the Hamiltonian acts only on nearest neighbors, and that defines the Hamiltonian. So that's the problem that condensed matter people study all the time. And if this were a random Hamiltonian of this type, you would just go to condensed matter department, ask them for a code that diagonalizes these operators, and that's the best you would be able to do. But here, this Hamiltonian has a remarkable symmetry that's not obvious from the way it was obtained. Namely, one can show that it commutes with an infinite number of extra charges that form an integrable hierarchy. So the claim is that if you define a charge that's built from the same local interaction, but then acts on three neighbors, three sites, three nearest neighbors. So in a sense, pictorially, it looks like that. So we first consider interaction of two spins on the neighboring sites, and then they interact on the next to nearest neighbor sites, and then we subtract the same with an opposite order. So then we need to first interact these two spins, and then so this is the structure of Q, and the claim is that this charge actually commutes with the mixing matrix. It's a very non-trivial property. Takes a calculation to check. And also, one can construct higher charges that act on 4 spins on 5 nearest neighbors, and so on. And all of them commute among themselves and with the Hamiltonian, and a system that possesses such charges is known to be integrable, and there is a systematic way to find the spectrum for such systems using integrability. So I have half an hour, right? Maybe you can take a break for strictly 4 minutes. So, and start at 1/2 sharp. Integrability is a very powerful property that allows to compute the spectrum algebraically, essentially. But so the step-by-step derivation is really abstract, and I decided to avoid it, but instead simplify the problem a little bit, and then use some kind of physical intuition to arrive at the answer. So let's consider something that might be more familiar to you, and this is called Heisenberg model. So to define it, we can introduce a complex basis in the space of fields. So instead of real scalars, let's consider complex ones, Z, W, and Y. So please tell me if you don't see very well, because it's like, for me, these letters, they look really huge, but I guess from a distance they might not be very visible. So so we introduce this basis, and we can also introduce the complex conjugate fields. And let's consider a subsector of the spin chain that only involves two complex scalars and is holomorphic. So we consider operators. This is called an SU2 subsector. So we take a product of L minus M Z fields and M W fields, and also we need to consider all possible permutations. If you look at how the Hamiltonian looks, you'll see that this is a closed sector. The reason is that it's neutral under traces. So trace acts really on these operators because trace contracts fields and their conjugates. So the trace operator doesn't act on holomorphic operators. And so the only thing that the mixing matrix will do is it will permute the fields in some way. And it simply permutes nearest neighbors. So the Hamiltonian is simply lambda over 8 pi squared, sum over L of 1 minus permutation acting on sides L and L plus 1. So to visualize these operators, we can represent them by spins. For instance, we can picture Z. Z is a matrix in the adjoint representation of SUN, but we represent it by spin up. And W we can represent by spin down. And then a trace in which these operators are multiplied in some way, we can represent by collection of spin-ups and downs distributed over one-dimensional chain. So this is the something wrong. So this would be each operator would correspond to a distribution of spins in a one-dimensional lattice, And spin can be in two states, up and down. And the Hamiltonian simply permutes nearest neighbor spins with weight -1. There is even a simpler way to write this Hamiltonian. We can introduce Pauli matrices that, also standard Pauli matrices that act on spin up and spin down. And then one can show that the Hamiltonian can be written as an interaction of spins and the nearest neighbor sites. So this simply means that we are dealing with a ferromagnetic spin chain. Why ferromagnetic? Because the energy is negative for parallel spins. So it is energetically better to align spins in the same direction, right? Then this will minimize the energy. So this model, it was proposed by Heisenberg in 1920, I forgot, 25, something like that. And it was exactly solved by Bethe, by the method that is called Bethe ansatz. So he was at your age at this time. He was a beginning graduate student. And he was invited by Fermi to visit Rome. And I don't know who gave him this problem, but he just solved it in a very straightforward way here. Found an ansatz for the, well, ansatz is a German for substitution. He found some form of the wave function that he liked, substituted in the Schrödinger equation, went through the algebra and found the answer. But there is a nicer algebraic way to solve this model, which I will not describe because of the lack of time, but rather will reproduce Bethe solution from simple physical intuition. So how would we go about solving this model? Well, we need first to find the ground state, which is, well, simple in this case. It is state with all spins up. So obviously permutation invariant, and so the energy of the state is equal to 0. By the way, for physical reasons, of course, this form is much more clear. But when you do explicit calculations, it's easier to deal with permutations. So this state is an eigenstate of the Hamiltonian, and it has energy 0. By the way, let us renormalize the Hamiltonian just to take out this factor of lambda over 8 pi squared. So the ground state we know, and then what would be the elementary excitations over the ground state? Well, these are particles that propagate along the spin chain known as magnons, and they're constructed in a, well, in an obvious way. So we can flip the spins one by one. So for instance, we can consider a state where we just flip one spin. with some weight that depends on the position where we flip the spin. How should I write? It's so this is the lowering operator acting on L side, and so the state will contain well, one spin down in the sea of spin ups that propagates with some wave function psi of lambda. Now, if we act by the Hamiltonian, then if we act at some random place in the spin chain, nothing will happen because permutation doesn't change the spin. So the only interesting thing happens when we act next to the spin, and the Hamiltonian either moves the spin to the left or to the right. So it's easy then to see that the wave function, the wave equation for the wave function is basically the discrete Laplace equation, discrete Laplacian acting on the wave function. And the solution, which can be anticipated on general grounds, is simply plane wave, where the substituting it in the Schrödinger equation gives the dispersion relation. Well, magnets essentially are non-relativistic particles. So if you draw this dispersion curve as a function of momentum, the momentum is confined to the Brion zone from minus pi to pi. And at 0, it's just, well, the dispersion is simply p squared, is like for a non-relativistic particle, but then it curves down and becomes a periodic function of momentum as appropriate for a lattice, for a particle that propagates in a lattice. All right, so, but in principle, the lattice should be periodic. This is a solution on an infinite lattice. And periodic boundary conditions are very easy to impose. We simply need to quantize the momentum. So periodicity means that we want the wave function to be periodic, and that happens if the momentum is quantized in the units of inverse lengths of the spin chain. Okay, so this solves the problem for one spin down. Let's then solve it for two flipped spins.
Hi, sorry, before we proceed, it's just on the mixing matrix there, shouldn't it be just the identity on the ground state?
In which equation?
Oh, no, sorry, never. On, okay, ground state, gamma equals lambda over 8 pi squared times something, right? Okay.
Here?
No, never mind. Never mind.
Where? That's the definition of what is H.
Oh yeah, this was in general, right? Yeah.
Rescale the energy. So I don't want to deal with this factor of lambda over 8 pi squared, so to write it all over the place. So the energy of the magnon then is p squared without the prefactors.
We could construct everything with spin down also, right? Means your ground state could also
Yes,
extinct,
yes, of
right?
course.
So it's like there is degeneracy. Like
Of course, yes.
okay.
So this there is actually the whole, like the states form SU2 multiplets. So there is the whole multiplet of spin L over 2. And the states in this multiplet are magnons with zero momentum, right? So if momentum is strictly zero, energy is zero. So if you propagate this spin with zero momentum, so the psi is literally equal to 1, then the energy will be still 0. And if you can do it with 2 magnons and so on, and that would produce the whole multiplet of that connects this all spin ups to all spin down. So for 2 magnons, we again can write the wave function, generic wave function that will depend on their positions, but we can sort of anticipate how it should look from solving the 1 magnon problem. So if they are very far apart, then nothing should happen, right? So the wave function should be just oscillating exponential. And so we can start with the following ansatz. Yeah, should I write on? Yeah, maybe I should write in the middle. So what is the meaning of this ansatz? Well, this is 2 magnons moving with momentum p and p prime. Then one can imagine that they will eventually collide and scatter off. And when they scatter, they essentially exchange momentum. So this is the scattering piece of the wave function, and it is multiplied by some factor which we can expect to be phase. And so this is just the scattering phase of two magnons. So then we need to substitute this into the Schrödinger equation, heat this by the Hamiltonian, and then we immediately see that as long as L and L prime are not nearest neighbors, this ansatz will go through the Schrödinger equation by default. Because, okay, so let's imagine that there is one magnon here, then some spins up, and then another magnon. And the Hamiltonian will only act here and here. And obviously, it acts in such a way that the presence of the other magnon doesn't matter. So this plane wave ansatz, this and this, will go through the equation. And so in particular, it will tell us that the energy of this state is simply the sum of energies of individual magnons. So the only case where interaction between the magnons is important is when they come as close to one another as possible. So when they're sitting on nearest neighbor sites. And then suddenly the Hamiltonian doesn't act on the side between them. Yes? Yes, thank you.
Similar to?
Should be sigma minus L, sigma minus L prime acting on the, yes. All right, so then the Hamiltonian will act only here and here, but not in between. So this case is special, and we need to write the wave equation for this case separately. So then what we get is 2 psi L plus 1 minus psi L minus 1 L plus 1 minus psi L plus 2 should be equal to E psi LL plus 1. Where psi is just this, well, what stands in front of the sigma matrices. So you substitute this expression here, and you see that what you will get is one equation for one unknown, which is the S matrix. So I'll not go through all of this algebra. It's pretty long, but just elementary. And write down the answer that comes out. So this fixes S, which turns out to be of the following form. So this is the S matrix. And then the next step is that we need to impose periodicity conditions on the magnons. So this, well, for two magnons, it's a bit tricky because you see here we have a condition that one of them should be to the left of the other. But when we pull the magnon through the chain, they interchange positions. So this has to be taken into account. And periodicity conditions look like that. So psi of L prime L plus L should be equal to psi L L prime, right? So we shift one magnon by L sides, the interchange position. So it's the same as interchanging their positions. And another equation, the same but with L prime. You substitute the wave function, and what you find is a set of two equations for the momenta. So the meaning of this equation is actually very simple. So if this S matrix were equal to 1, this would have been the same quantization conditions that we imposed on the momenta of a single magnon. But now when we pull a magnon around, we need to take into account that it hits another one. And then it acquires a scattering phase. So the total phase that a magnon gets when it goes around the spin chain is a combination of the oscillating part from its wave function times the scattering phase shift. And that's the equation that you get. Now, what Beta did is he went to 3 magnons, 4, and so on, and then he found an ansatz for the wave function for an arbitrary number of magnons that is built precisely the same elements, the same S matrix and oscillating factors, plugged it in the Schrödinger equation, and found all the coefficients, and then found periodicity conditions that are known now as beta equations. But the physical meaning of these equations is very simple, so I will not go through all this algebra and simply write down the beta equations themselves. Yes? These are not the same equations.
I just mean S is clearly symmetric between P and P prime above.
It becomes S minus 1, right? So it flips.
Sorry. Yeah, sorry, you're right. Yeah.
So the intuition here is the following. So if you take a system of n magnons, and then you pull one of them around, its wave function will acquire pairwise interactions with all other magnons, and also the oscillating piece. So what comes out then is a set of equations for momenta that are simply periodicity conditions for the wave function of each individual magnon. And then the total energy of the state is simply the sum of energies of each of the magnons. So these equations are known as beta equations. To write them down, To derive them, you need to do a lot of work. But to write them down, you only need to solve a two-body problem. So you find the S matrix for a magnon scattering on a magnon, and that's the only ingredient that enters the beta equations. To find the energy, you also need the dispersion relation. You may ask, and what about integrability? Where had we used it? So integrability here is very important because integrability tells you that all interactions are pairwise. There are no irreducible triple interactions between magnons. So in an arbitrary spin chain that's not integrable, these equations would have been awfully complicated because you would need to consider triple collisions of all magnons, and essentially it becomes a mess. And solving this system for a non-integrable case, you need to redo calculations so to repeat the derivation of Schrödinger equation for each number of magnons independently. But for an integrable system, it's enough to solve it for two magnons and then recycle this in an n-body problem that can be solved at once. All right, so on the next lecture, I will tell you how to extend this to SO6 and how to, for that one needs to write it in a little bit nicer form. So thank you very much. That's
So somehow the dispersion relation does not change. It's just addition of energies of different magnons. Somehow they don't interact and reduce the energy in any way. Like for the wave function calculation, there are beta equations, but the energy seems to just be additive.
So this is easy to understand because if you separate them, in this case where we have two magnons, when they separate, the Hamiltonian acts on them independently. So the sum so the energy has to be the sum of the energies.
But when they're but we would expect interaction between magnons only when they're closer or something like that, right? So
yes, when they come closer to one another, they start interacting. But that determines the structure of the wave function and affects the periodicity conditions.
I see, but there is no function that we could, or maybe I don't know, I would think that there should have been some function which goes to 0 in the limit when they are separate and which is non-zero when they are close or something like that. A function of ij, something like that.
Well, I mean, here the interactions are strictly local, right? So they only interact when they are sitting precisely next to one another. If the interactions were decaying with the separation, then yes, there will be some function interpolating between them. But for superlocal interactions, the energies have to be additive. Okay. It's
thanks.
Yeah, I was wondering, how can one prove that the states you've constructed here form a basis of the Hilbert space of the problem?
Can be done. It's not an easy exercise. Can be done algebraically. I don't have time to describe it, but
okay.
There is the whole algebraic framework, which is not based on this simple physical picture, but you can construct an algebra that's more or less like Heisenberg algebra. It's creation and annihilation operators. And then using these algebraic properties, you can prove that this state formed the complete basis.
Right, okay. But so this proof has been done, okay.
Yes, it is done, yes.
Okay, thank you.
So I was wondering, in this construction of the Heisenberg spin chain that you made, it seemed to me that basically you wrote down the model and then you found out that it is indeed integrable, and it has this behavior of being, all of its dynamics is reducible to solve the two-body problem, and then everything follows. So my question would be, what is the minimal condition for, given a model, I can say, okay, this is integrable?
You have to find an extra charge, an extra operator that computes with the Hamiltonian. That's not obvious, an obvious symmetry. Like here, there are some obvious symmetries, translational invariance, SU2. If you manage to find something that doesn't look simple, but commutes, that's enough for integrability. So this charge that I wrote here, also for the Heisenberg model, it commutes, and it suffices for integrability.
How we can check integrability of a system from holography, from gravity point of view?
Sorry?
How we can check integrability of the system from holography, like in some gravity calculations?
Oh,
Here
yes.
It's like Heisenberg picture, spin chain.
Yes, good. That's so one would, if one tries to quantize the string, so fix the gauge and then write down the, let's say, equations of motion of the string, it turns out that it is integrable in the same sense. So there is an infinite number of charges that are conserved, which are not geometric.
More questions? Well, if not, let's thank Konstantin again. And we'll be back in half an hour.